If I told you that your whole perspective on areas was about to change, would you believe me? What if I told you that you've been doing calculus since grade school? In fact, finding the area between two curves is truly elementary. Stick around to find out why. Here we go. Hey, thank you for sticking around. It looks like you're ready to have your mind changed. Think back to a class where there was a big chalkboard in the room. I bet it was a lot of fun to draw on it with the different colored chalks. And on holidays, you might find an intricate drawing in the corner of the board, like a big jack-o'-lantern, or a turkey, or autumn leaves. This could have been drawn by your teacher, a multi-talented janitor, or maybe even that classmate you secretly admire. But one thing is for certain, to shade in an orange pumpkin, it is most effective to place your chalks alongside on the board and drag it that way. This is where our analogy begins, with chalk. We've all seen this trick, where you place a piece of chalk on its side on the chalkboard and drag it to make a long shaded region. This is how an area is made. Your chalk has a length, say 2 inches, and you drag it along a chalkboard for a certain distance, say 5 inches. The shape you create is a rectangle with area 2 times 5 inches squared, or 10 inches squared. But why is this so? What's really going on here? In particular, how is the region getting shaded in? Your chalk has length 2 inches, right? And when you drag it over to the right, you start to get some shading. The shading has vertical length of 2 inches, also. It has the length of your chalk. And when you continue to drag the chalk for the full 5 inches, we find that everywhere in your rectangle, there is a vertical length of 2 inches. So, in essence, there is an infinitesimally thin chalk imprint on your rectangle, and these collectively form your 10-inch squared rectangle. But how many razor-thin chalk imprints do we have? Well, we have one for every point in the closed interval from 0 to 5 inches. And so we take our chalk of length 2 inches and multiply it by the length of our closed interval to create an area of 10 inches squared. And that's it. That's how we find the area of a rectangle. But what was special here? Well, the length of the chalk was always 2 inches, so every infinitesimally thin chalk imprint had vertical length of 2 inches. What if the length of the chalk changed as we moved from left to right? We could still go over the closed interval from 0 to 5 inches, but this time the top of our chalk would either grow taller or shrink. And at each point in our interval, we would get a razor-thin chalk imprint over that point, although this time the vertical lengths are changing. However, we still see that we get a shaded region, and thus we still get an area. Well, can we take this a step further? Yes, not only can we grow and shrink the top of our chalk, but we can simultaneously change the bottom of our chalk as well. And the process of dragging the chalk over our closed interval still holds valid. So, let's say the top of our chalk is given to us by a function t of x, where x is in our closed interval from 0 to 5 inches. And let's say that the bottom of our chalk is given to us by a function b of x. Then the length of the chalk is just t of x minus b of x. In the case that our chalk was just a fixed length of 2 inches, we would have that t of x equals the constant 2 and b of x equals the constant 0, so that t of x minus b of x equals 2. It was also the case that the area of this rectangle we drew was 2 times 5 inches squared, or 10 inches squared. What this number really is the integral from 0 to 5 of 2 dx, which is equal to 2x evaluated from 0 to 5, or rather 2 times 5 minus 2 times 0, or 10 inches squared. So, you've been doing calculus since the first time you played with chalk, and this is why the area between two curves is truly elementary, because it's just equal to the integral from 0 to 5 of the length of our magic growing and shrinking chalk with respect to x. That is, the integral from 0 to 5 of the top of our chalk minus the bottom of our chalk with respect to x. The area of our shape is just the collection of infinitesimally thin chalk imprints over our interval from 0 to 5. And that's it. But wait, there's more? Yes. Actually, this idea works universally in the following sense. If we use the chalk normally, as in to draw a line segment on our chalkboard, then what we are doing is making an infinitesimally small point imprint on our chalkboard for every point in a closed interval. And so we get a line segment of length of that interval in inches. And if we could somehow take our rectangle that we drew earlier and pull it out of the board by some distance, say 3 inches, then we could create a rectangular prism with volume given by 10 inches squared times 3 inches, or rather 30 inches cubed. And so we find that we can take an n-dimensional shape and drag it through another dimension to create a shape with inside measurement of inches to the n plus 1. In particular, we could drag a 3D cube through the 4th dimension and create a 4-dimensional hypercube. Crazy, right? What other crazy shapes can you make? Can you describe how to make a 9-dimensional cube using this method? Let me know in the comments down below. But with that being said, the area between two curves is just like shading a region on a chalkboard with magic growing and shrinking chalk. And that's it for today. Math, just like anything else in life, gets easier the more you see it. Take, for example, your favorite movie. I bet you could watch it for the 9th time and still find some new Easter egg in it. So, now that you've seen this video n times, see if you can fill in any gaps by watching it n plus 1 times. And if you have any questions, be sure to leave a comment down below. If you found this video helpful or interesting, be sure to give it a like, as it helps support this channel. New videos are posted every Tuesday at 2. To never miss out, be sure to subscribe and hit the notification bell. Thank you so much for checking out this week's video. See you Tuesday!